So we have seen how to exploit buffer overflows. Now I will try to tell you how to prevent those guys and how to find buffer overflows and related security problems in your source code, or if you are too lazy to find them, how to apply dynamic countermeasures so at least the exploitation wouldn't be so easy. We're already pretty tight with time, and so I hope I will get through my slides. If not, we have to cut the dynamic countermeasures a little bit short. Then you should come to me after the talk and I will give you a private lecture. About me, my name is Martin Jons. I work at the University of Hamburg as a security researcher in the project Psychologic. Psychologic is a project carried through by SAP, the Commerzbank, a company called Eurosec, and us, the University of Hamburg. And we try to, in this project, we try to establish what is the state of art in software security and how can we widen the boundaries so that our software gets more and more secure every time. If you're bored at work or if you're really interested in the topic, go to www.psychologic.org. We have quite a couple of nice white papers on C security, PHP security, and Java, and everything, pretty much. Okay, what I'm going to talk about. I will show you tools that are applicable by the programmers. So I'm not interested in stuff that the person can do that is installing the program or that is administering the server. I only want to look at, when I am the programmer, how can I be sure that my code is not as exploitable as it used to be. Most of the tools I'm going to show you have their origins in academia. This is one simple reason. Those tools are published and we can look into the way they function, and it's more interesting to talk about something we understand than something we don't understand. These are the commercial tools. There's quite a limited market space for commercial tools to do static analysis for security reasons. But I don't know how those tools work, and I can't tell you anything about them, what you can't get from the website. So we just look what is possible in academia today. Pretty much everything I tell you today is aimed at a C language. The main reason is that the most papers that have been published are concentrating on the C language. There are a couple of reasons for this. The main reason probably is that the most severe security problems today are still rooted in the C language. C gives the program so much access to the underlying computer memory structure that an unsecure C program allows a lot of exploitation. If you go to Bugtrack and look for buffer overflow, heap overflow, or format string, you're going to find something pretty much every week. Also, C is pretty easy to check. I think this is one of the reasons why a lot of tools look at C but not C++. The control flow of a program, so the stuff that is happening when the program is executed, is mostly determined on compile time. You have something like function pointers, but they are not as heavily used as in, for example, object-oriented programming. And C programs are often vulnerable at a quite easy, unsophisticated level, at a syntactic level. So a lot of problems are caused by library functions like string copy. And so if you look at all the string copies, you may have a good idea where at least a couple of your security problems may lie. C is also quite hard to check. C depends really heavy on pointer arithmetic, typecasting. So seeing what data you have and where the data is going during your control flow is really hard with C. Also, C programs, especially bigger projects, do heavy use of the preprocessor. So I've seen projects, they seem to program more with the preprocessor than with the actual language, so this might be a problem for static too. And we also have more than one C. We have ANSI C and KNR C and blah blah C. And so if you do really sophisticated analysis, you sometimes are not really sure which semantics are behind those statements you're looking at. The tools we're going to see are not only concentrating on buffer overflows, but we also have tools that look for exploiting of heap corruption or format string exploits. Just a warning, you pretty much all know now about buffer overflows. I hope you believe me there's something like heap corruption, format string exploits, and that the tools look for this. I won't go into detail why they are vulnerable or how to exploit them. Just believe me, they exist. To make it a little bit more accessible, I have done a classification. The main classification is between static and dynamic tools, as I already told you. Static tools do the check before or during the compilation. Dynamic tools work on runtime. They compile some code in the user executable that is supposed to find or prevent exploitation. This is what we're going to cover in the next hour. At first, we start looking at syntax-oriented tools. Those tools work because C is usually, or C is often, as I told you, exploitable or vulnerable on a syntactic level. So if you look at all the unsafe library functions that don't respect buffer boundaries, like string copy and everything else, we're going to find a lot of problems already. So this is static tools that look at work on the syntactic level pretty much only do that. They look in the source code, are there string copies, are there gets operations, are there printfs with a dynamic format string, and they're going to warn you about this. So these syntactic tools pretty much work only on a per statement basis. They don't take any context in account. They look just line for line in the code. Oh yeah, there's a string copy. We may have a problem here. They don't really work on the source code per se, but they do some pre-processing. They generate a token stream, an abstract syntax tree or stuff like that. But this is as sophisticated as it gets. I've got here 3 examples for you, Floor Finder, ATS4, and REDS. If you're interested in this kind of analysis, all 3 tools are free, so you can go to their websites and look at them. And they're kind of useful if you have a really small project or if you're just starting your programming day. And if you're not really familiar with which library functions may cause security problems, they give you a pointer to problems in your code. But they're not really interesting. Limitations of syntactic analysis, I think I've told you a little bit about already. They take only limited context into account. So they may look at type qualifiers. A string copy with a constant source may still cause a buffer overflow, but this buffer overflow is pretty surely not exploitable, so we don't need to look at this in a security context. And some tools on the syntactic level do some other preliminary checks, but they're not really sophisticated. They totally ignore complex context like inter-procedural dependencies. They don't calculate the control flow or the data flow of our program. So the consequences is pretty obvious. We get a lot of false positives if we use these programs. For example, Floor Finder reports pretty much every single string copy in our code. Doesn't really matter if it's exploitable or not. A false positive is an alert from our program that says, hey, here's a security problem, but actually there's none. So even if our program is totally secure, Floor Finder might warn us about 500 times. Other syntactic analysis or other problems that may lie on a higher semantic level. So stuff that is caused because of a sequence of instructions. For example, a double free problem. Syntactic tools are not able to find those problems. The next type of tool is on the next. I have 2 examples for this. Are the compiler-related tools. If we look at compilers, especially at modern compilers, we can do a general observation. Static analysis tools and compilers share quite a lot of common techniques. A compiler does parse the source code into an abstract representation, token stream, abstract syntax tree, or something more complicated. Even our syntactic tools do this. For optimization reasons, they generate control and data flow graphs. This is something we could use for static analysis for security reasons as well. And they do enforcement and check of constraints. For example, even a CSON compiler does some type checks, so we are not able without typecasting to assign integer value to a character variable. So the more advanced our compiler is, the more the compiler does understand the program and does understand the semantics of the program. And if we want to do some sophisticated analysis for security problems, we should understand or should try to understand our program. So looking at compilers can help us. The first real tool that I'm going to show you is called Boon. This is short for Buffer Overrun Detection. It's from the year 2000. Boon introduces for its for its analysis a theoretical abstract data type called C-string. As you probably all know, C doesn't have a data type string per se, but it only has character buffers and a couple of library functions that work on this on these character buffers. And so this is the only things that Boon looks at. It looks at the way these library functions work on the character buffers and if they may cause security problems with buffer overflows. Boon ignores control flow, but is still able to do some interesting observations. It's done via integer range analysis. So for every C-string, as we have in our program, Boon creates two variables, one alloc s and len s. Alloc s represents the integer or the range of memory that is or that may be allocated in the memory for this C-string. Len s represents the min and the maximum amount of memory that is actually used, so how much bytes are actually written into this buffer. The safety property is pretty obvious. If for one of our C-strings the maximum value of len is bigger or equal to the minimum value of alloc, we might have a problem It might be a situation where we write more into the buffer than we have allocated space, and so we have a buffer overflow. The analysis itself is done via integer range algebra. So we have one operation that we're going to look at. This is the operation contains. Actually, contains works on the second argument. If you have two integer ranges A and B is supposed to contain A, the analysis looks at B and tries to widen the boundaries of B if A exceeds those boundaries. For example, we have an integer range A from 2 to 5, and we have a constraint that says A should contain at least the range from 4 to 7. After this operation, A will equal the integer range from 2 to 7. So for every statement in our program code that work on the C-strings, the program or Boon constructs an integer range constraint. For example, if we have a C-string S and we allocate 6 bytes of memory for this, we have the constraint that the integer range alloc of S should at least contain the integer range 6 to 6. If we read into this buffer with fgets, fgets reads from 0 to a maximum number of bytes, in this case n. We know that the length of S should contain at least the range between 0 and n. Not so fast. And string copy, really important one. If we copy from source to destination, our range that is constrained, or the constraint is constructed, is that the length of the destination should at least contain the length of the source. How this is computed, I'm going to show you a little bit more in detail. After the program has constructed all those constraints, a direct graph is built. The vertices of this graph are our variables, and the edges are the constraints. And remember, the constraints represent functions or function statements of our program that work on those buffers. So this is a really, really small program that we try to construct the graph for. We have 4 vertices. This is our 4 variables: length for source, alloc for source, length for the destination, and alloc for the destination. The first statement in our program constructs 2 constraints, 2 interrange constraints. So the length of our source string should contain at least 13 to 13, and the allocation of our source string also should contain at least the range between 13 and 13. The second statement gives us the next 2 constraints. It's pretty obvious now. Alloc of destination should contain the distance between 8 and 8, because we allocate with malloc exactly 8 bytes of memory. The length of destination right now is still in the range between 0 and 0, because we haven't dereferenced destination at all. The last line gives us only one constraint, that the length of destination should contain at least the length of the source. So